welcome to today's webinar. My name is Matt Bemis, and I will be your speaker and presenter today. This webinar will focus on the design and optimization of data centers. So we will be looking at airflow throughout a data center, actually going into SimScale and showing you what the setup is, as well as doing a design iteration, making a few modifications to try to improve the performance of the data center. Lastly, of course, we'll take a look at some results and understand if that iteration we did indeed improved the design. Just a quick note on myself. So I've worked at SimScale for about 3.5 years as a application engineer within North America. And previously, I held a few other positions, mostly doing CFD, working with a few other companies, doing some CFD consulting as well. My background is in mechanical engineering, and that is me. So let's jump into it. I'd like to just quickly go over the agenda for today. So first, if you are not familiar with SimScale, we'll do a quick overview. I will keep it brief, to make sure, I think most of the team probably here knows SimScale. After that, we'll really try to understand why actually simulate data centers. So what are the problems that arise in data centers? How can SimScale help? And what does that mean to you? So how does that make your life better? During the live demo, we will look at a sort of a classical design. So it'll be an underfloor, raised floor data center with downflow CRAC units. You'll basically understand or come away from this webinar understanding what it takes to do CAD prep, how to set up and really do best practices within SimScale, and then as well how to compare results and understand, really make design decisions. We will have time for Q&A at the end, and if you are interested or when you are interested in checking out SimScale, I'll give you some next steps as to how to sign up and get started. So a little bit about SimScale. SimScale is the first browser-based, completely cloud simulation tool, the CAE tool. What that means is really anywhere in the world where you have an internet connection and a laptop, you can run high-fidelity simulations. This is very unique. I thought it was unique 4 years ago when I joined SimScale, and it really I actually come from a desktop-based CFD background, and I think probably everyone here knows the bottlenecks there. So only being able to run one simulation at a time, maybe having to use a TeamViewer, Microsoft remote desktop to check on your simulations. These things I have not done since I joined SimScale, and you would not have to do if you decide to use this tool. So our goal is really to allow anyone and everyone to have access to simulation and make it feasible. And by feasible, we mean it's not impossible to use. You can get up and running quite easily, and it is not prohibitively expensive. So that's the background on SimScale. Next, let's talk about data centers a little bit here. So pretty much everything on the cloud is actually hosted on a data center, as we know, I'm sure. And they use an incredible amount of energy. Now, about 30% of total data center electrical consumption is due to the cooling, so due to the HVAC. When you look at a global scale, maybe that's whether within the US or worldwide, that is a massive amount of electricity. This is, of course, emitting greenhouse gases, and it's expensive, right? So there's huge opportunity to optimize data centers, save money, really improve your energy use and try to minimize your energy use, and just make smarter designs. Now, more specifically here, what you'll often see in a data center is problems like recirculation of racks. So you've got hot air blowing out the back of a server. It's recirculating on itself, going back into the inlet. Now, data centers are considered mission critical, and what that means is 365 days a year, 24/7, they need to be up and running. Usually, most data centers I've actually worked within usually have 3 instances to allow for redundancy. It is just never acceptable to have downtime, and that is avoided at all costs. So this means they need to stay cool as well. So usually these have very, very large CRAC units, computer room air conditioners, and they are blowing air, usually down into a raised floor, which is what we'll look at today. And then airflow. What we see on the right is airflow coming out of the floor tiles in front of a server. So we'll understand, do we have recirculation? And ultimately, we're actually going to look at adding in a return ceiling plenum. Now, ASHRAE actually has a standard for rack inlet temperature, and we'll understand our adherence with that criteria. So ASHRAE actually says have the rack inlet temperatures between 64 and 80 Fahrenheit. Ideally, it'd be great if you could balance the room perfectly and have everywhere in the room at rack inlet be 80. But in real life, what you're going to see is, well, it's 64 somewhere and 80 somewhere else. So trying to even those up and then actually raise your thermostat is kind of the name of the game here. I want to give an overview of today's actual data center. So what you see on the right is the geometry we will be working with today. So this is a raised floor data center with about a 1.5 foot raised floor plenum. We've got 16 racks here, servers, and each one of them, or 16 cabinets, I should say, each one of them has 42 U's. And again, just for anyone who may be a little new to this, a U is basically a slot. It's roughly a couple inches, and that's usually where a server would sit. In terms of energy density, we've got 8.4 kilowatts per rack. That's actually on the high side, really, for designs that maybe don't have a more sophisticated cooling approach. But I guess we're going to see if we pull it off here and understand if we can maybe improve the design a bit. Now, the cold air, I will supply it at 70 Fahrenheit. Sometimes you walk into data centers and it's really cold. You want to put on a sweatshirt. It shouldn't be necessary. So the thermostat supply air here is going to be 70 Fahrenheit, about 21 C. And a few kind of drilling down into specifics. The questions we'll be asking ourselves: okay, what does the rack inlet temperature look like? Not only what does it look like, does it meet the ASHRAE standards? Does a ceiling return plenum improve results? So if we have areas which do not adhere to this ASHRAE spec, does a ceiling plenum help? Also, do we have recirculation on racks? If yes, does a ceiling plenum help there as well? I think that's a fairly good overview. And of course, we're going to one of the parts I'm most excited about is actually doing a demo. So we'll jump into the platform and I'll show you actually how I set this model up. Later on, it'll be posted online. You can check it out. Copy my project, make this, make changes and run it again. So I'm pretty excited about this, and I think we can keep on moving here. So the whole point of simulation really is to, as a application engineer, I always say it's a bit of a failure when someone just runs one simulation. That means they're using it in sort of a validation check approach here. Really what I want to see designers doing is running a whole bunch of simulations. That means they are getting creative and trying different approaches and understanding how that affects performance. On the left, we have the initial design. So what this means is we've got a room return. So the air goes through the racks, becomes hot on the hot aisle, and then room returns. Now, what's interesting on the left is we've got a pretty, there's not a lot of space above the racks. Pretty tight room. If you are going to go with a room return, it's always great to have tall ceilings, but a lot of times that's just not a reality. Now, on the right is the new design iteration, and I've added in a ceiling plenum. So if you're not very familiar with this, what we're doing is we're actually putting in a ceiling, basically a false ceiling, and we put in tiles in the hot aisle. So just due to buoyancy, essentially, and some fan power from the CRAC unit, we'll pull the hot air up from the hot aisle into the ceiling plenum. We'll find out, this should reduce recirculation on the racks. And then I think probably one of the most important parts is you'll notice over on the right, the CRAC unit is actually, it's essentially attached to the ceiling. So It's got a duct there that attaches right to the ceiling, so it only pulls that hot air, and it provides suction in the hot aisle. Of course, here we do see that um, that floor plenum, so it's worth checking out there. That's where these are, of course, downflow cracks. Just in case anyone's kind of new, the general airflow direction is clockwise. So in both models, it doesn't really matter. We've got a downflow air conditioner supplying cold air. Going into the floor plenum, there are floor tiles in front of the cold sides of the racks, and that cycle repeats. So let's jump into the product here. And so I'm going to pop out of my window and jump into SimScale. So this is the SimScale interface. I did just hide my my URL here, but it's really important to note I'm just in Google Chrome. I'm using a standard Lenovo laptop. You don't need, there's no hardware requirements, really. I've never run into a hardware limitation. And you just need a half decent internet connection. So nothing special. Residential Wi-Fi is more than enough. That's actually what most people use here. So having a look at the, I guess the part A or where we start is always with geometry. Now, the good news here is I know a lot of the data center sort of industry uses Revit or AutoCAD. The great news there is we support those tools natively. Really, we usually say at SimScale, if you have a CAD, we can work with it essentially. I would say the one necessary requirement here is it needs to be 3D, and you're not going to make your CAD within SimScale. But besides that, we'll pretty much work with it. So most people use Revit, and taking cloud to the heart, I actually use Onshape, which is where I built this geometry. But it doesn't really matter where you make it. Let's actually look at the no containment solution. So if I hide a couple faces here, I'd like to, actually, I'll just hide the walls. We can just have an understanding of the basic setup of the model here. So in the navy blue, we've got our CRAC units down, flowing or blowing air, cold air down into the return plenum. I'm sorry, the floor plenum. And then on the people always ask, how do you actually define a rack and what's that look like? So there's a couple different ways, but the way we're doing it today is essentially the cabinet itself, the black black part is just a frame, very simple. We do have this sort of teal color on the front and back. These will actually be a cabinet door, so we're going to assign a porous media on them and say, hey, if you've ever been in a data center, usually the cabinets actually usually almost look like a speaker cabinet you may see in like an upscale speaker system. But lastly, once we get through those, we've got the core, and really that is a block which is representing all the servers. I'm not actually going down to the U level. So the way we will, and actually the way most data center modeling is done, is we're going to say there's a uniform 8.4 kilowatts on this rack. It's not how everyone does it, and SimScale certainly supports going down to the U or 2U level, server level, but it takes more time to set it up, requires more information too if you're using DCIM tools to pull that information. It becomes a lot more. So SimScale actually, there needs to be a bit more of CAD processing. We do have a CAD mode here, and what we need to do is extract a flow volume. So that's essentially an air volume, which represents the flow region. And it's sort of like a negative of this model you can see here. Now, I'm going to jump, let's not worry about that for now. I've already done that, and what you end up with is something like this. So if I hide the air volume, we see we still have the servers, and we still have the racks and floor tiles and so on. And if I actually just hide the external surfaces, we kind of have a negative where those CRAC units are. So we're in good shape here. Let's go ahead and create a simulation, and I'll show you how I set this model up. I'm going to use the convective heat transfer module. This basically just means we have a nice description here, but there's natural and forced convection within an air volume. We'll create a simulation, and you'll notice there's a simulation tree on the left. Our job is really to work down this. We have a few missing pieces of information, which are indicated by red circles. So for example, materials or boundary conditions. Ultimately, we're trying to get down to simulation runs, where we will kick off a simulation. Now to start, I am actually going to set the gravity direction. You'll notice there's a view cube in the lower right corner. All we're saying is down on the screen represents gravity. In terms of boundary conditions, we will be defining a supply flow rate on the underside of the CRAC, and this will be a volumetric flow rate here. So I'm actually going with about 3.92 cubic meters per second. We do support different units, by the way. I'm kind of mixing and matching to my liking here. But I'll call this CRAC supply. Great. So each one of these 3.92 cubic meters per second, supplying at 70 Fahrenheit. I have to repeat the process for the returns. This needs to be a velocity outlet, flow rate, volumetric, 3.92. Great. So we've defined the CRACs. Now we need to work on really the racks. And so we've got a few parameters under advanced concepts. And I am going to go a bit quicker here, but we're going to work with the porous media a few times. I'll start with the floor tiles. And so if you've ever seen a floor tile, you would not actually, in the simulation world, bring in the geometry with all the holes. Instead, you're going to say, hey, you know what, approximately this is 30% open. And so we'll define this here. And SimScale will approximate with very good accuracy the pressure drop through the floor tiles. Next, I'm just going to repeat this process, but for the doors, cabinet doors. These are usually a bit more open, and so they are on the front and back. By the way, SimScale does have a box selection. I guess I'm kind of doing it the old-fashioned way here. Now, these are usually about 60% open, and the flow's in the X direction. Excellent. All right, so we're good on porous media, and we've got a few more things to define here. So very quickly, I'm going to actually hide the cabinet door so we can get to the actual server part here. And we'll do a power source. Again, this is going to be 8.4 kilowatts, and it's going to be uniform on the volume. Now, momentum sources, just being cognizant of time here, I'm going to set up, let's say, a few of them here. So let's just worry about the first aisle. We're going to say in the Y direction, the flow rate is approximately 33 centimeters a second. You can usually get this off a spec sheet on your servers. It's just an approximation. All we're saying is, hey, there's internal fans in these servers, and they're moving air here. So that's really the setup. You'll notice I have green check boxes the whole way down the model here. And again, for the sake of time, I'm not going to do all the momentum sources. Let's jump up to my setup here. I've already run this analysis. It takes less than an hour. And if I were to start it again, we just get an approximation. Okay, run to. We even give you an estimate, which is very accurate in this case. It tells you how long it may take. Once we hit start, the simulation gets offloaded on our cloud. You can go back to working in Revit or do something else. So I already ran this analysis, and I've already done some some visualization or post-processing. In this case, I actually took a bunch of screenshots, already shared it with colleagues, and had some interesting findings. Here we're looking at velocity, and really we're just seeing velocity come out of the floor tiles. So this is really almost what I expected, and a very classical thing you can see in data centers. If we focus on the far right, we have pretty good velocity coming through the floor tiles, through the servers. The hot aisle is always developed by having servers face each other, and that forces, airflow hits, and the airflow goes up, hits the ceiling. And the problem is here, instead of going back to the CRAC units, it recirculates on itself. So we see it in every single aisle here. For example, over here, we see the airflow come up, hit the ceiling, head towards the right, come back down, and it just recirculates on itself. This means maybe if you're supplying at 70, your servers, especially the ones at the top of the rack, are not going to see 70. They're going to see 70 mixed with 90 or something like that. Hopefully, we'll check it out in a minute. Hopefully, a ceiling plenum will actually resolve this issue. I had to look at a few other things, so I think probably what's most pertinent is looking at the particle traces, understanding if this has the same effect. This pretty much confirms what we already knew from the cutting plane with the vectors. This tells the exact same story. So again, let's focus on far right. We have the airflow come up through the racks, goes through the particle traces, hit the ceiling. If focusing on the far right, this is a clockwise sort of issue where the airflow is just recirculating back through the rack. So this is a huge problem. Sometimes data center operators, try to combat this by setting your supply airflow cooler, driving down the thermostat. It's really just it's an expensive patch. That's not, you don't need cold air. You need less of your hot air going into your data center servers, into the inlets. Now, I think that's interesting. And we've got quite a few different options here to check out. But I think what is most interesting to me is actually this image here. Now, it may be a little confusing at first because we only see green or red, but I think this tells a very interesting kind of tale of what's going on here. So earlier I mentioned that ASHRAE standard. Essentially, it says airflow needs to be, for Fahrenheit, between 64 degrees and 80 degrees Fahrenheit at rack inlet. Now, SimScale allows you to modify your legend and the min and max number of levels, and I dialed this into sort of a yes or no. I guess it's too cold, good, and too hot. So we got three options here. Green means we're between that 64 and 80. We don't see any blue, but a lot of times data centers are too cold. And red means you're too warm. I think the areas that really jump out to me, let's say right here, if you see my cursor, I guess the farthest to the left row, and it's always the rack at the end of the aisle, right next to the CRAC unit. Now we've got too warm of an area here on the right side of the rack. Same story, a couple rows down here as well. Essentially, one of the tough things or challenging as a data center operator, it's not, you may have DCIM infrastructure in there, you may have sensors in there. It's not one value, it changes based on the position. And that's where CFD and SimScale can really give you insight. So again, we've got problems on the rack, which is closest to the CRAC units. Just check it out the opposite direction. Tells the same story. These are the problematic racks here. Now I'm going to jump up and kind of just show you my ceiling return design. So if we go to the CAD, essentially what's going on here, we already saw the slides here. So let's just quickly have a look at what's going on in here. Well, of course, skip the setup. It's very similar. So I think if you understand one, you'll understand both. And I guess the primary addition is now the the ceiling actually kind of looks like the floor as well, right? We've got these tiles up here. The hot aisle has the airflow go up into the ceiling plenum, and then the CRAC units are ducted to the top. And so let's jump into results. Look at the ceiling return. And I think probably what is the biggest, well, we'll take a look at a few options here. So particle traces, this is fantastic to see. Focusing on the far right, we don't have any of that recirculation. What we see here, I've hidden the ceiling, but it's where you can sort of see the ceiling tiles. No recirculation. The airflow just goes straight up into the ceiling plenum. And checking out some of the other, let's actually have a look at the ASHRAE conformance. So essentially we're good at the end of the aisle here. Really the only problems, I guess, that the top corner maybe, but I wouldn't worry about that too much. We see a lot more green than we do red versus the original design. Here's the kind of the first view we checked out. Looking at that rack closest to the CRAC units, we're good. So that had the desired effect. And I think just looking at vectors here, we don't see any of that recirculation as well. So I'm trying to be cognizant of time. Let's jump out and go back to slides. I'll have a few moments here for Q&A and some other things as well. So before we dive into Q&A, I would like to just kind of recap on what I showed you today. So we had a look at a classic raised floor data center, which has downflow CRAC units and a room return. We had some issues on ASHRAE conformance at the rack inlet temperatures. Specifically, the racks closest to the CRAC units were a little on the warm side, and instead of just driving down the supply temperature or putting more air into the room, both of those are expensive. We thought, well, maybe if we just put a ceiling plenum in, can we actually improve the performance with the same amount of air, the same amount of cooling capacity? Ultimately, it worked. The answer is yes. We put in a drop ceiling, and essentially we're able to get rid of that recirculation you see on racks, which is excellent. So let's jump into Q&A and go ahead. Please feel free to write in questions which you may have. So I see someone asking, all right, so someone asking about the CAD geometry, which is excellent. So I'll answer this so everybody can understand. So with SimScale, you do need 3D geometry. So most of our customers who are using SimScale today for data center analysis are using Revit. We also support Rhino, and if you happen to be using a mechanical CAD program, we pretty much support all of them. So SolidWorks, Onshape, Inventor, and so on. You're not going to build 3D CAD within SimScale. That's really, we leave that to the CAD companies. And what else? I think it can't be 2D. It does have to be 3D. So I hope that that answers that, and we can move on to other ones. Let's see. So I've got a couple questions here. So number one, does SimScale support fan curves for the CRAC units? That's a great question, and the answer is yes, which is pretty exciting. That's actually pretty new. So as a boundary condition, instead of just saying, okay, the flow rate is 3.92 cubic meters per second, we all know these CRAC units, sometimes the underfloor plenums can get too busy, have too much stuff, and the supplied flow rate is less than maybe what's spec'd. So you can define, we call it a fan boundary condition, and this will allow you to upload a CSV file defining flow rate versus static pressure. You can certainly do that. I encourage you to check it out. I'm excited I've been using it, and it's a great feature to have. Someone else is curious, will this video be available to view later? So it absolutely will. All of our webinars we sort of post-process and then put online for viewing. So please check it out. It'll be up in a couple days. You can check out our website and see a previous recording. Now, another question. So the model I showed you today we basically went to the rack level. So the detail, we said uniform distribution, 8.4 kilowatts. The question is, can we actually go down to more detail? And that answer is yes as well. So I've actually had customers, I think I mentioned this originally was a 42U rack and server cabinet. People have actually model all 42Us, or sometimes they're the 2U slots, so they do half of that. You can do that. So usually where this is most relevant is when there's a high amount of power density at the top of the rack, and down below usually there's blanking or something like that. You can add in that detail. It's always a balance, because you will have to CAD that, and then you'll have to set more boundary conditions, more heat loads. So the answer is yes to that as well. I think lastly, can we get hard data? So points, if I have a sensor somewhere, can we actually get like an exact value for temperature? You can actually drop in a CSV file of XYZ coordinates and drop in, we call them probe points, sometimes call monitor points. You'll get a graph of temperature versus iteration. It's great for checking out convergence, and you can download that data and bring it into Excel and look at the agreement. So absolutely, I would encourage you to do so. And that wraps up the Q&A. So that's all I had to go. That's all I had today. Thank you very much. And just going over next steps. So you can request a demo, whether it's by myself or someone on my team, by just going to our website, simscale.com, or contacting us directly by email, sales@simscale.com. We'll get in touch. You'll be able to jump on a call with an application engineer, and we'll understand, what problems you're trying to solve and whether we can help or not. So that's all I had for today. Thank you very much for attending. And as I mentioned previously, this will be available online for viewing as well. Thank you.